So in class for chapter 2.3, we talked about the following objectives. We determined if a relation is a function. We used the vertical line test to determine a function. We evaluated a function. We determined the x and y intercepts, and we determined the domain and range of a function. So now we'll go to our first problems actually. Our first objective is determine if a relation is a function. So I want to go back down here at the bottom of the page, and the definition of a function is given a relation in x and y is a function of x for each value of x in the domain. There is exactly one value of y in the range. So if we look at our first problem, determine if the following set of pairs are a function. What I'd like you to do is to pause the video and see if in fact you think this relationship is a function. Then I would like you to do the second problem. Determine if the following set of pairs are a function. I will pause. So to see if a set of pairs are functions in x and y, I create a table. So what I'm going to do is I'm going to create an x table. Or actually, I'll just do a column. And I put y here, and I see I have 2, 9. I have a minus 1, 4. I have a minus 2, 5. And I have a 3, comma, negative 1. Well, we can see in this particular case for each value of x, there's only one value of y. So this is a function. This relationship is a function. Now we're going to do the same thing for the second pair. Hopefully I can do this without too much trouble. I get a minus 1, minus 4, 0, 0. I get a minus 1 and a 3 and a 2 and a 5. Well, so far we have a minus 1 to a minus 4. We have a 0, 0, but now we have a minus 1 to a 3. So our problem is right here. We have one value of y going to two different values of y. Two values of x going to two different values of y. So this is not a function. So our next objective is to use the vertical line test to determine a function. So we have the equation x squared minus 4 is equal to f of x. And we want to determine if this equation is a function. So I'd like you to pause the video, and I would like you to create the equation or graph the equation on the graph, and then we want you to figure out whether or not this is actually a function. So now I will show you what I would do in this particular case. I would graph the function. And the way I graph functions is I look at, I let f of x or f of 0, and I evaluate it, so I have 0 minus 4. So I have a point at minus 4, 0. So when x is 0, I have a minus 4, which is 1, 2, 3, 4. So I have a point right here for my equation. And then I call that the y-intercept. And so now I'm going to let 0 is equal to x squared minus 4. So now I have 4 is equal to x squared, and plus or minus the square root of 4 is equal to x. So x is a minus 2, and x is 2. So when y is 0, I have a 2, and I have a minus 2. And this equation is probably continuous, so I can graph it, and it is a parabola. And now I will use the vertical line test to see if, in fact, I have a function. So if I draw a line anywhere on this equation, I see that I only intersect the graph at one point. And so because of that, this equation now is a function. So this is a function. So in objective 2 is continued. We're going to determine if the following graphs are functions. I would again like you to pause the video and see if you can figure out which of these graphs are functions and which are not. Okay, so you should have found that there is only one function in these three graphs, and it is number b. B turns out to be the only function. Y, well, if we draw a line anywhere for the circle, we see that we hit the circle at 2 points, so this is not a function. For B, you can see I can hit different spots on this particular graph, and I see that this is a function because I only touch the equation at one point. Now C is kind of tricky, and the reason it's tricky is it's tricky at the y-axis. And in this case, if I draw a line right here, I touch it at 2 points, 2 interval points. So this one is not a function. So in this case, we're going to evaluate a function, and what we mean by evaluating a function is for a particular value of x, we're going to put that value of x into the equation or function and evaluate it. So We have two functions here. We have f of x is equal to x squared plus 3x, and we have k of x is equal to the square root of x plus 1. So I'd like you to pause the videos, and I would like you to evaluate these functions at -1, 3, and -2. So now we're going to look at how to do this. We're going to first look at the first function, f of x is equal to x squared plus 3. And we're going to evaluate it at -1. So f of -1 is equal to 1 squared plus 3. And you can see that this is 4. At f3, we get 3 squared plus 3 times 3, and this is equal to 9 plus 9, which is 18. And finally, we'll look at f of -2, and here we get a -2 squared plus 3 times a -2, and this is equal to 4 minus 6, which is equal to a -2. So there's our function for f of x equals x squared plus 3. Now we're going to do the same thing with the other function. So I'm going to draw a line here. And now we have k of x is equal to the square root of x minus 1. And now we're going to evaluate it. Oh, well, we should have done it this way. K of -1, right? So that equals the square root of a -1 minus 1, or plus 1 actually. Oh, I forgot. This is a plus here. So we have the square root of 0, which is just 0. So we now have k of 3, and we get the square root of 3 plus 1, which is equal to the square root of 4, which is equal to 2. And finally we have k of -2, and we may have a problem here. -2 plus 1 is equal to the square root of a -1. So here's a restriction. We can't do this under the function rules for real numbers. So you can't evaluate a -2 for that function. So our fourth objective that we discussed in class was determine the x and y intercepts. And you will recall from a previous discussion that to find a x-intercept, we want to let f of x equals 0, right? And to find y-intercepts, we let x is equal to 0, right? We let x is equal to 0. So I'd like you to look at these three functions. G of x is equal to 3x minus 12. And b is qx is equal to a minus x squared plus 9. And c is s of x is equal to the absolute value of x minus 2 minus 1. So I'd like you to pause the video and determine the x and y intercepts for each of these functions. So now we're going to look at the first function. G of x is equal to 3x minus 12, and we'll find the x-intercepts first. So the x-intercepts, I'll just put x-intercepts. There's probably only one in this case because it's linear. So we have 0 is equal to 3x minus 12. 12 is equal to 3x, right? So, oh wait a minute, this is the y, no, this is the x-intercept. So x is equal to x is equal to 4, right? The reason why this linear function, you say, oh well, so the x-intercept is at 4, so the line goes through the x-axis at 4. Now the y-intercept is very simple, because in a linear equation, you know that this is the slope and then this is the y-intercept, right? But if you let x equal 0, you have g of 0 is just equal to a minus 12. So in this case, the y-intercept is a minus 12, right? And that crosses the y-axis at minus 12. So the x-intercept for the next function, again, we'll let 0 is equal to a minus x squared plus 9. And now we have a minus 9 is equal to a minus x squared. And now we divide by a minus 1, or multiply through by a minus 1, and we get 9 is equal to x squared. So now we take the square root, and we get plus or minus 3 is equal to x. So there are our x-intercepts for the q of x. And for the y-intercept, right, we have q of 0 is equal to 0 minus 9. So in this case, y is equal to a minus 9, right? In our y-intercepts, we should really put out where the intercepts are at. It's at 0 minus 9, right? And our intercepts over here are 3 comma 0 and a minus 3 comma 0, right? And we can identify these functions. This is a linear function, so it would be a line, and this is, of course, a parabola. Our final function is an absolute value. And so again, when we set for the x-intercept, 0 is equal to the absolute value of x minus 2 minus 1, we have 1 is equal to the absolute value of x minus 2. And now x minus 2, if you can remember, x minus 2 can equal 1, or x minus 2 is equal to a minus 1. So this means that x is equal to 3, or x is equal to 1. So our x-intercepts are going to be 3, 0. That's where it crosses the x-axis, or 1, 0. And now we can find the y-intercept by setting x to be 0. So s of 0 is equal to the absolute value of 0 minus 2 minus 1. So this is equal to the absolute value of minus 2 minus 1, which is just equal to 2 minus 1, which is equal to 1. So our absolute value in this particular case is 0, 1. Our fifth objective is to determine the domain and range from a graph. So for the following graphs, A, B, and C, determine the domain and range and put the answers in interval notation. So go ahead and pause our video and see if you can come up with the domain and range for each one of these particular graphs. So we'll go ahead and do the domains for A, and here we look at the graph and we can see that there's a parabola, and we ask, is there a restriction on the value of x? And in this case there's not, so we know the domain is all real numbers, and for our particular case we have for interval notation we have parentheses negative infinity comma infinity parentheses. The range now, we can look at the graph and we can see that the graph for the parabola ends at y is at 2, and then it goes more positive. So in this particular case we have a bracket and it starts at 2 and it ends at infinity, right? So that's our domain and range for A. Now we take a look at B, and we see that the values of x, if we go along the x-axis, there doesn't appear to be any restrictions on x, and again we have the real number set. And if we look at the range values along the y number line, we see really, in some sense, we cover all of the y number line. Even though there's a disconnect on the y-axis, it doesn't really make any difference because the rest of the line is covered over on the right-hand side. So we look down and we see that it looks like minus 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. At 10 is where we start our graph for the y number line, and we started at a minus 10, and it appears to go continually positive. So this looks like that is our range values. C is kind of interesting in that we have an endpoint. We have an arrow going in the negative direction, but for x, we're only going to look at the x number line right at the moment. It goes negative, but then it stops. It looks like it stops at 1, 2, 3, 4. So in this particular case, we have all values going in the negative direction, but it stops at positive 4. So we have a bracket that closes. So that's our domain for C. Now let's look at the values on Y. Well, here we have, we see that we can hit 1, right, for Y. And then we go immediately to 2 and then on up to 4. So in this case, we have, essentially, we have the value, the following value. We have 1 for Y intersecting with 2, and it goes up to 8. So it goes to 8. And so there's our range values for this particular problem. See, we have a number 1, right? It goes to 1, Y, and then it goes from 2 to 8 on the y-axis. And we use this, and I should do this better. This is the union symbol, and the union symbol is this union of two sets, right? So these two sets have are combined to create our range values. So again, our last objective is to try to write the domain in interval notation. So we're going to look at this, and we have a function f of x is equal to x minus 3 divided by x minus 4. For b, we have g of t is equal to the square root of 3 minus x divided by 5. And for c, we have s of t is equal to 6 divided by 4 minus the absolute value of t. So I just want you to write the domain. We're not going to talk about ranges here, just the domain. And I want you to pause the video and do the domains for each one of these functions. So we'll look at number A first, and we ask the question, is there a restriction on x for the domain? And the answer is yes, and we can see that x cannot be 4. So to write this in interval notation, we know that x can go in the negative direction up to 4, but it can't include 4, so we have to put the parentheses. And it can go after 4 up to infinity. So this is our domain for the first one. For the second one, we ask again, is there a restriction on x? Well, we have a square root function, and in this particular case, x cannot be greater than 3, right? It cannot be greater than 3 because if it is a greater than 3, we have a negative square root, and we can't graph that. It's an imaginary number at that point, so there's a restriction. So in this case, x can be negative, right? So it can be a negative infinity, and it can go up to 3, but it can't go past 3. So here is our domain for that function, right? Just the domain. Now let's take a look at problem C. Here we have an absolute value t on the bottom. So we say, oh, gee, t can't be a negative 4 or a positive 4, right? So now in interval notation, this is how we will represent this. So now we can say, okay, we can go from a negative infinity, right, up to a -4. And now we can go from a -4 to a +4, but we can't have 4s, so we use that. And then finally, we can go in the other direction, 4, infinity. Looks like a lot of ink is being used for this interval notation, but there it is. There is the notation for our domain for S of t. So this concludes our in-class discussion on writing domains. And so I'd like you to practice the lecture problems and some extra problems that were on the syllabus for this section.